Okay, hello, this is Bob Jackson. I'm with you with SE 202. This is chapter 16, Earth, actually on the Earth's surface, and we won't get into talking about earthquakes. Okay, and the cause of earthquakes and what happens because of earthquakes. So it can be an interesting one where it gets real interesting if you get more interest in this is what I typically in a classroom, although not doing that with this course, is build on top of this in a STEM classroom is to put some STEM activities like earthquake engineering, and that's where you can do bridges and buildings. And you just buy balsa wood, a cheap balsa wood, and have student competitions where they build bridges and build them earthquake proof, and you have a way that you go through testing them and see which kids build the strongest bridges. The bridge building one is a really good activity. I highly suggest it. And then you can also do buildings where you build like skyscrapers, and then you essentially shake them through earthquakes and see whose buildings stay up and who's come down. But those are fun activities for kids. So, but anyway, this chapter is just on where we get into the some earth science, and we talk about some basic features of the Earth's surface and talk about the things that go on to cause earthquakes. Okay, so like I say, it is chapter 16 in your book, and let's go. Some of the first things we're going to do is talk about what's introduced in the other chapter was continental drift and your crustal plates, your main plates of the major 7 plates that make up mainly the continents of the world, and where you have like the North American plate and the South American plate and so forth. Well, within those plates, within the crustal plates, we've got a lot of activity, and there's certain regions of the world that see more activity than others. And some people that live in California and out west, even up in Alaska, they have a lot more activity as far as earthquakes and even volcanoes are concerned. And then Hawaii, some people have been stationed in some places around the world that have a lot more activity as far as earthquakes and so forth too. So anyway, you do start out really, and this is carrying on from talking the crustal plates. Okay, and we're going to get into the plates, and that's what you're seeing on this slide. They're just kind of cross sections of a crustal plate. These can be many different types of rock structures. Okay, that can change from place to place, and it's all according to where it is, and whether it's mainly sedimentary rock or you got a bunch of granite or what have you. But the same processes can take place within any type of rock layers. Okay, so there are 3 major stresses that are always going on under their surface. Okay, and it's all about rocks. Okay, you have tension. Okay, you have tension and tension. You see it as a pulling apart process, and that's what you're seeing here. And as a result, you see on the image here, you see that it becomes concave region, like a big valley. And that's what you naturally see in those areas on the Earth's surface. And they can be very wide areas where this happens, okay, or where it has happened through millions of years. Okay, then you have compression taking place where they're compressing the rock layers together, and you get this happen. And that's where you start building some mountains and building some hills and structures like that. And then, of course, you have some that were built and then they got weathered down through time too, which is another level that you can go. But the whole point is there's there's a type of process that takes place in Earth that you call compression. That's where you're compressing the rock structures together, and as a result, you typically get some uplifted layers, and you can get what's called folding taking place, in which we'll see on the next slide or two. Okay, and then you have shearing. Now this is the one that's really common, particularly out out west in California with the San Andreas Fault, and that's shearing, where you actually have, in which it is a fault, and we will get to where we call them faults. Okay, and you can call them earthquake faults at that. But shearing is where your crustal plates will move opposite each other like this. Okay, very slowly through time. When they move quickly, because rocks, they build up stress and then just kind of blow apart, that's when you get an earthquake. Okay, where they're moving, and all of a sudden there's very little movement. That's what we're measuring all the time out there along them fault lines. If it's not moved for a long time and it's building up pressure, it's a good sign there's going to be an earthquake take place. But you call it shearing. Okay, and it's where the crustal plates move opposite directions of each other along a fault line or a crack in the earth, if you want to say. Okay, now then, this is a video here. I'm not going to play it, but it will. I'll just flip through it where they're um, showing you how each one of these take place in kind of a live animation. This is something that you might want to use with your classes in order to show how and what goes on with each one of these. Like here's tension taking place here, and here you get these areas where they're like valleys that form. Okay, and it shows animations of types of stress like here, and you can see after earthquakes and big earthquakes in areas where you actually get this taking place, and you get particularly sidewalks in towns and then roads, you can see where they got where the movement took place. Okay, so that's a good video for you to show simulation of each of the different types of stresses that can take place in rocks. Okay, on this one, this is talking about folds that take place in the crustal plates of the earth, actually the upper layers. And this is actually as a result of the strains and the stresses that take place that we talked before, but this is very specific, and they will call this an aplastic strain. And that's where when the stress has been put on these rocks, they get pushed upward, and then you see these layers, okay, of rock that get folded like this. Look like it's stacked up blankets here, okay? And what you see in real life, and you can see this particularly in one of the best places is Arizona and Utah, but I've also seen in various areas like Colorado where you see exposed rock in the mountains, and you see this. This is folding. Now there's terminologies for these geographical features, like where you have the hill formed and have this folding that's taking place within it, you call them anticline, whereas the valleys where this has occurred, because they're right next to each other, okay? A syncline is a trough shaped or a valley, okay? But both of them are folding, and both of them come about because of strains on the rock features through time. And this of course, get this raised up there took thousands and thousands of years. Okay, it didn't just happen overnight. Okay, now then, on this next one, we'll start taking a look at faults. After some earthquake activity, you can get new faults formed, and that's where you get breaks in the Earth's crust. And some of them can be quite large, and you can have smaller ones. Okay, like in this hillside here, this cliff, these are faults here where these rocks are broke apart just on a smaller scale, but this is huge. Okay, here's a fault here. This is the San Andreas Fault in California. Okay, But faults are just fractures in the Earth's crust. Okay, and there are different types of faults, and we're going to talk about those. Okay, so here's the types. You have a normal fault, an oblique slip fault, a reverse fault, a thrust fault, and then a strike slip fault. And the names actually tell you what they do, except for really normal, I guess. It is by far the normal one is the most common out there, I guess what you'd say. But with each sets of crustal plates that are come together and they have a fault between them, a big crack between them, you have you have a foot wall and you have a hanging wall, okay, in juxtaposition to each other. Okay, now then, if you look at a normal fault, this is what they call the normal fault. Okay, and you'll see that the hanging wall block is moving downward. The foot wall block is moving upward. Okay, and that's the main part of the definition of them. And it's just this movement. Try to get my hands place out. It's just this movement on these at this fault that is talking about. We're going like this. You get a general with the foot wall block, you get it pushed upward. Okay, and you will see that on the ground at the site. Okay, whereas an oblique slip fault, you're looking at the very same type of thing, but you also get the sideways movement here. See, this block went that way, as well as you got it sliding down. Okay, so it's doing two movements. Okay, that's the oblique fault. Okay, then you go a reverse fault. It's called reverse because it just does the opposite of what a normal fault does. You're this, okay, and well, and that other thing I'm leaving out here is like this fault is where overall these plates are moving away from each other in a normal fault, whereas in a reverse fault, they're moving the plates on the overall on their surface are moving towards each other. Okay, and pushing inward. Okay, but what you see the movement of these plates here. Where see how the hanging wall leaves a overhang like this here. Okay, that's a reverse fault. Okay, the hanging wall block moves up relative to foot block. Okay, then you can have this as a thrust fault here, whereas a thrust fault is a reverse fault. It's just that this angle here is at a very low angle compared to this. This is steep, this up here like this, thrust faults like this, and this plate, this top plate here, can actually kind of slide over the other and more. That's a thrust fault, it's thrusting itself over. Okay, and then a strike slip fault, okay, that's where your plates are moving like this. Okay, okay, I'll put my hands so you can see they're moving like this relative to each other. Okay, and that's what you got going on with the San Andreas fault in California. Okay, it's a strike slip fault. Okay, now in earthquakes, okay, and most people know what an earthquake is. It's shaking of the earth. Okay, it's vibrating. Something's making that happen. Usually it's because some big, massive rocks have hit together and are breaking apart, and causing things to get shook around quite a bit. Okay, earthquakes cause seismic waves. Those seismic waves are making everything shake. Okay, now then some terminologies with earthquakes. You have the focus. Okay, the focus is an actual spot in the earth where the earthquake took place. Like if two rocks broke apart in that movement, if they suddenly broke pieces off and just there was stress, and they broke and they all of a sudden went, that's down in the earth's surface. Okay, now that can vary how deep that is or how close it is to the surface. Okay, and that's what determines a lot of how intense it is. Okay, so the focus is down in the earth. The epicenter is on the earth. So when they refer to the epicenter of earthquake, it is the point on the earth right above the focus, okay, where the earthquake took place. Okay, epicenter's on the earth, focus is down in the earth. Okay. Now your seismic waves, there's some different types of seismic waves that come off of an earthquake, some that are extremely destructive and others not so. Okay, so first you have P waves and S waves. They are down in the Earth's surface. Okay, the P waves are body waves. When we say body waves, that means they're in the Earth. Okay, they're taking place in the body, in the Earth. The body is the Earth. And they travel very fast, and they will travel through any type of medium, solid, liquid, or gas. Okay, and they propagate longitudinally, which they're moving outward. Okay, but they cause very little damage because they're down within the earth, and we can measure them, but they're not the ones really causing the damage. Okay, and then S waves are also down in the earth. They will only move through rock structure. Okay, they won't move through water, they won't move through the air. Okay, P waves can move through the air. Okay, and you can actually feel them in the air above the ground where they take place. Okay, S waves also cause very little damage. Okay, and they are slower. They are a slower wave. Okay, than the P waves. The ones that are going to hit the surface the first after earthquake starts are these guys. Okay, but then the real devastating ones are the waves that are taking place on the surface, on the flat surface on the top of the earth. Okay, and we call them surface waves. And they're surface waves because they're taking place on the surface of the earth, or what's going on with the surface of the earth. The waves are taking place on the surface. And there's two main types of those. There's love and Raleigh waves. Okay, and now then they started saying love, it has nothing to do with love. The guy's last name that defined these is Dr. Love. Okay, and same thing with Raleigh. Raleigh was a PhD that worked with these and studied them, and they named them after. Okay, so they are named after two guys. Okay, love waves are surface waves that move. That they're moving like on the image here. They're moving sideways. Okay, so they're moving like this. Okay, and it's really shaking things around. Okay, they're not doing this. Okay, they're doing this mainly. Now it's looking like this because these love waves are taking place the same time the Raleigh waves are. The Raleigh waves, you will see them visually as just like water waves. But what you got within the earth is elliptical motion in those waves. It's almost a circular pattern like this and will roll across the surface of the earth. That's where these doing their number, doing this, and the Raleigh waves, giving the big rolling waves, is what brings things down. Okay, brings buildings down, brings bridges down, and causes mass destruction on their surface. Okay, and that's, I mean, they're it as far as, and that's why, because of these, earthquake engineering has come about, a huge area in civil engineering anymore where they try to build earthquake proof buildings and bridges more than anything. Okay, and can be interesting stuff because building things to withstand these waves is something pretty phenomenal, really. They got bridges on most that'll float and move as the earth shakes. If there's rigid, they'd fall down. Okay, measuring earthquakes, we measure earthquakes with the Richter scale. Okay, again, named after a man back in time. Okay, it is a numerical scale. Okay, but now then, what people don't understand about the scale, and I'll explain to them, is there's a huge difference in each level on the Richter scale. It is a logarithmic scale. So like a 3, if I have on the Richter scale, Richter magnitude of earthquake of 3, and then one that's 4. 4 is 30 times larger magnitude of an earthquake than a 3. Okay, so particularly when you get on up to 6, 7, and 8, each step up is 30 times more magnitude. So that's where when you get up here to 7 and 8, you get total destruction, because each jump up the scale is 30 times more powerful. Okay, so the Richter scale goes, I mean, you could take it on up to other. I don't know of any in our time that we've had earthquakes over an 8. Okay, but you have pretty massive destruction at between 6 and 7 even. Like we've seen with Japan several years ago, and they lost the nuclear reactor there and all. Okay, so we measure earthquakes with the Richter scale, and I think it's kind of neat to show kids that and show them how we actually measure them. Okay, and that's it. That's the lecture for for chapter 16. I'll be back at you with chapter 17. Have a good week.